In this last video, at least for today, we're going to look at types of proofs or proof structures that often break down into cases. So where we have to prove multiple things within the proof. What kind of statements do those apply to, and what forms do they take? So in particular, this applies to statements, propositions involving equivalences, and ors. So those are the things to look out for in the statement that might imply that cases are going to be needed.
All right, so a lot of these are pretty straightforward, and we're going to go over them relatively quickly. There are two ways to prove an equivalence statement. So you could prove it directly, starting either with P or Q. Let's just say P. If I only use logical equivalences at every single step, everything I say is an if and only if statement. And if I can do that and go from P to Q, then I have proven P is equivalent to Q. But often this is a challenging approach. Okay, so often it's hard to only use logical equivalences in our reasoning. So the second option is based on the logical equivalence of P, the biconditional, P if and only if Q is equivalent to the conjunction if P then Q and if Q then P. Okay, and so option 2 is basically just two proofs in one. So you're going to start, suppose, you could use direct, you could use contrapositive, you could use contradiction, but somehow you prove if P then Q is a tautology, and then you have your second proof where you prove that if Q then P is a tautology, and therefore it follows that P and Q are equivalent. So it's really two proofs in one. All right, so bonus proof. Now, what if you have a chain of equivalences? Something like P, the following are equivalent. P, Q, R, and S are all equivalent statements. Well, one way we could approach this is I need to show that P is equivalent to Q, and that would involve potentially two implications, to showing P implies Q and Q implies P. I would need to show that P is equivalent to R, and again, that could involve two proofs, and P is equivalent to S, which again could involve two proofs. But I would also need to show that Q is equivalent to R, another two proofs, and Q is equivalent to S, another two proofs, and R is equivalent to S, right? And again, another two proofs. So this could be as many as 2, 4, 6, 8, 10, 12 proofs here to show this chain of equivalences. But do not worry, it is not that bad. Really, all we have to do is show that one implies the other. P implies Q, Q implies R implies S, and you do have to close the loop. S implies P. Then because implication is transitive, if P implies Q and Q implies R, then we know by our rules of logic that that's enough to conclude P implies R. And similarly, if P implies R and R implies S, that's enough to conclude P implies S. And we can similarly trace around. S implies P, P implies Q gives us S implies Q, S implies Q, S implies Q, Q implies R, that's going to give us this other direction, S implies R. So just proving this circle of implications is enough to prove a series of equivalences. So that's what we're going to do. We could rearrange them. We could do P implies R implies S, S implies Q, Q implies P. You can, any arrangement where we kind of close the loop is what we would need. And so we see for this one, it's going to be, in this case, 4 proofs in one. So if I'm using this ordering, I would first prove somehow that P implies Q. I would then prove somehow that Q implies R, then somehow that R implies S, and then somehow that S implies P. And note, you need to make sure all these proofs are independent, so that at no point in these proofs are you assuming anything other than what has already been proven here. Okay, other instances where we have multiple proofs in one, or not. So let's look at statements involving ands. If I have the statement A and B implies Q, it's a conditional claim here, right? So how do we prove that? Well, if I want to do this directly, I'm just going to suppose the premises. Here the premises are A and B. So I'll suppose A and B, and then just create that chain of logical implications and equivalences until I get to Q. So this is really just one proof, but I have more starting assumptions. So this could be easier than just proving A implies Q, something like that, or B implies Q. So this really isn't a different technique than just our normal conditional proofs techniques. We just have a different set of premises. However, if the statement is P implies A and B, this is 2 proofs in one. Okay. This is logically equivalent to the statement P implies A and P implies B. And so you're going to have to do those 2 proofs. Doesn't matter which one you do first, but you're going to need to show P implies A and P implies B. And so I haven't written down the starting points and ending points because it would depend on how you do it, right? So for example, you might do this directly, in which case you would suppose P, right? And then get your chain of logical implications and equivalences until you conclude A. And maybe this one is easier to use the contrapositive, in which case you would suppose not B and do your chain of logical implications and equivalences until you deduced not P. So you can use either technique. You could prove one of them by contradiction. You have lots of options here. Okay, how about statements involving ors? So this is, as we've seen with and ors, there's often sort of a similarity but a difference, a parity in approaches. So when we had an and in the premises, we saw that was just a very straightforward approach. However, when we have an or in the premises, that's going to act a lot more like the and in the conclusion. So an or in the premises is logically equivalent, saying A or B implies Q. And that's equivalent to saying A implies Q. Excuse me. And I should say, B implies Q. So again, we have 2 proofs in one, or 2 cases. We need to prove A implies Q, and then we need a separate proof to show that B implies Q. And once again, you might approach these proofs, you might approach the statement, you could use direct proof, you could use contrapositive, you could use conditionals. If there are quantifiers in the statements A, B, or Q, you might be using some sort of existence or instantiation proof. You have lots of options there. All right, what if the statement is P implies A or B? How are we going to approach that? Well, one thing to keep in mind, again, is that this is just a conditional statement. So this really is no different than our discussion about proving conditional statements. We just have a more complicated conclusion. And it is hard to conclude in or, right? if you just think about how you might do that, it's not as straightforward. But we don't have to prove this directly. I don't have to start with P and conclude A or B. I could use contrapositive or contradiction. So let's look at what a contrapositive or contradiction approach would look like. So contrapositive, I would be supposing not A or B, which we know is equivalent to not A and not B. Okay, so that's a nice assumption to start with. I have two pieces of information because they're connected with a conjunction. So I get to assume both not A and not B are true. And then from there, I can take any series of implications or equivalences that allow me to deduce not P. Okay, and then I could say, therefore, by contrapositive, P implies A or B. What would contradiction look like? So for contradiction, I'm going to suppose not P implies A or B. Okay? And so that is the supposition P and the negation A or B, which is the same as P and not A and not B. Okay, and just a note, I've written this out. I should make this clear. This is actually what I would suppose. This is where the proof would start. So I would just suppose this statement by way of contradiction, I should say. Oh my goodness. So suppose by way of contradiction, P and not A and not B, but that's valid by these logical equivalences. Similarly here, this is what I would suppose, which would be valid because of this logical equivalence. Okay. So back to our proof by contradiction, having supposed P and not A and not B, I just need to reach some sort of contradiction, and then I can conclude that P implies A or B. Okay. There's one more approach to a statement of the form, some conditional, P implies a disjunction, A or B. And that is based on the logical equivalence of P implies A or B, or if P then A or B, is logically equivalent to the statement P and not A implies B, which is also equivalent to the statement P and not B implies A. So since all these statements are equivalent, you can prove any one you want, and it will prove all three of them. And we see that these two later forms are much easier to work with. So rather than having to conclude an or statement, I get to start with a and statement. So I have two pieces of information, and I have just one conclusion I am trying to reach. So here, let's just pick one of these. I'll pick the P and not A. So we would suppose P and not A, and I just need to show that that is enough to conclude B. Okay, and that would allow us to say, thus, P implies A or B. All right, so you have quite a few options when you have a disjunction or an or statement in the conclusion.
I hope these videos have given you a good start in recognizing different proof structures and recognizing some of the statements that you might apply them to. So again, things to look out for. If you are struggling to get from your premises to the conclusion, especially if it's a conditional statement. Maybe contrapositive or a contradiction proof is going to give you better premises to start with and an easier to reach conclusion. Another thing to note, again, you always want to start by simplifying any negations in your statement, but concluding a negation or a lack of something is always hard. So it's hard to prove something doesn't exist. It's hard to prove something isn't a definition often. These are not, there's a little bit of an art to this, so I can't say that this is always true. But it's frequently true that trying to conclude a not is a challenging thing to do. That's a sign that maybe contrapositive is going to be a better proof technique, because that concluded not, that not Q, or that Q you're getting to is some not. And so the contrapositive would allow you to suppose the negation of that. So that's a way of switching some statement that has nots in it into some statement that might be easier to use. So for example, if you wanted to, conclude that something is not divisible by 3, then if I instead approach it by contrapositive, I'd be starting with the assumption something is divisible by 3, and that's an easier thing to work with. And then hopefully the negation of the premises is also easier to reach. So some things to look for. We'll talk about this more in class, but I hope that helps get you started. And as always, let me or your professor know if you have any questions.